Hey everybody, and welcome back to Calc 3 Online. So today marks the start of a very important unit in this course where we're going to start really working with a lot of multivariable functions. So we're going to take derivatives of multivariable functions, which is something called a partial derivative. And like that whole thing is going to lead into integrals of these functions, and you'll see, there's a lot here. So to start off, I just want to talk about basically domain and range, which should be something that you're pretty familiar with. It's a little different, but I think it makes sense when I kind of explain it. You'll see why this just builds directly on what your notion of domain and range is. So basically a function of just two variables, like it says right here, we write it f of x comma y. And based on this structure, you can see like the input of it is going to be like a 2D region, right? So like the x comma y space there. And then it's going to output still to like z. And that's just like a number line. So the domain of the function is like a set, like, some 2D kind of region. Like a lot of times you're going to describe it with an inequality. And then it outputs the range here, which is like the set of all real numbers z. And they're just going to basically be something, up and down on the z-axis in a sense. So it's kind of like, if you think in 3D here, it's like the domain for this function up here, it's, some surface, is this yellow input 2D area in the xy plane. And then it outputs, up into z up here, different, output values that are like at different heights or whatever, and you get some sort of surface. The way you typically do this, so in, algebra 2 and stuff, you just describe the domain with interval and the range with an interval. You might use inequalities to do that still, but for multivariable functions, you really kind of have to describe the domain with an inequality, and you're going to still describe the range in terms of like an interval. And so, if we think real numbers for this function, we would want the inside to be greater than or equal 0. So we want all this stuff to be greater than or equal 0. And this is for the domain. And then, really we can just simplify this a little bit. So we could divide by 9. Then I would probably move the x and the y over. So I get that. So what this is, right, if x squared plus y squared equals 4 is a circle with radius 2, right, I guess I can draw it, that would be this circle with a radius of 2, then less than or equal to there, like x squared plus y squared being less than or equal to 4, just means we shade in the circle, right? So basically, my region down here is like a circle in the xy plane, and I'm going to map, to some, different z values, and I can just describe those in terms of basically an interval. And to do that, sometimes it's a little bit tricky, so let's talk through it here. So for we'll do a different color. How about purple? For the range, you basically have to look at the domain here and think about, what is the largest and smallest kind of values you can get. And you have, technically an infinite amount, but, the big changes are going to be when the numbers start to get like big or really small. Like, while they go out, you'll see a trend, and while they go in, you'll see some other trend, right? So if you plug in, if you go back to the equation, you plug in super small, like the smallest number possible with real numbers would be zeros, right? Because we're not going to be like squaring imaginary numbers and getting negatives and things like that. So the most that we could ever like make this thing is if we took away the least amount, right? So these need to be, basically zeros, and then we could get the most out of this function. So if you plug in 0, 0, to that function. I guess I'll just do it like this. This is the right way to do it. F of 0, 0 is literally just the square root of 36, which is 6. And you could never get more than 6 because as soon as you plug in anything else here, then you're going to be, taking away something more than 0. And so then it's going to get smaller and smaller. If you play around with some of the other numbers, like on the edge and stuff, you'll see that like if you do f of like 2 comma 0, let's say, then you're actually going to be, making this 4, and then 9 times 4, 36, you're going to get rid of that. And so you can get this square root, you can be square rooting like 0 in there and get 0. You can't be square rooting like, negative numbers and all of that. And so that's really like the lowest you can go. And so we can get to 0, we can get to 6. So if we use like that fancy interval notation I showed you last time, we would actually write it this way. But really it is just, if I use inequalities to be super clear, it's just the z values between 0 and 6. But really these are saying the same thing. So that's the range. And this is literally how you show the domain. You can just, you could say it like that, but picture is good too. Yeah. So you might think this kind of stuff is weird and, why would we ever even do functions with multiple inputs? But it actually turns out that most things in the world have multiple inputs. It's pretty rare to think of a problem where there's only one input. Like all the stuff you've done, honestly, up into math right now, like the idea of having one input and only one thing that affects this whole problem is kind of ridiculous. So there's tons of stuff in math where there's multiple inputs. Just to show you one, there's something called the distribution function, and it's actually a function of 7 variables. So it's got a function of x, y, z, which are basically like spatial positions, t, which is time, and then it's a function of velocity in the x direction, velocity in the y, and velocity in the z. And this thing is like really useful in tons of physics, but basically what it's doing is it actually gives you the number of particles per volume in a single like particle phase space. And the way I think about it is what's down here. So basically you're kind of curious about the velocity in the different directions when you're at a different point in 3D space at a different time, okay? And you don't need to know what this function really is, but this is just an example of one that actually I think is kind of reasonable to start to begin to understand. So there's lots of things out there where you're going to have a whole bunch of things as the inputs in here. There were a whole bunch of math problems I've done in my life where literally it starts off like this. You have f of x1 comma x2, and then you just go dot, 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 x sub n. And you basically have to understand that as like an infinite amount of different inputs. And there's a whole bunch of problems where if it scales up nicely for like n-dimensional inputs, and then we can like prove some sort of like big general concept regarding that function, that's like super useful to us in math. So this kind of stuff just shows up everywhere. Just erase that, don't worry about it. And they do have names, these different kind of functions. So like when you do have one input, like your f of x stuff, we call those things curves. Actually, even a line is called a curve. It just has curvature 0. So those are the things like in R2 that you're used to. This is basically, all the math that you've seen, literally. 2 inputs, which is what we're going to kind of start off with, are surfaces, that's what we call them, and they're graphed in R3. 3 inputs are actually called hyper surfaces. That really is like a formal term, and they're graphed in R4. And sometimes students think this is space-time, but space-time is a 4-dimensional construct, but I am talking literally about the spatial 4th dimension, which is different than space-time, which is something else kind of. And we don't need to get into it too much, but I am literally talking about like if you to build dimensions in math, like 1 dimension, 1 number line, 2 dimensions, 2 number lines, 3 dimensions, 3 number lines, 4 dimensions, it gets really hard to draw, but like you have to draw another line that is perpendicular to everything else, basically, which I can't do on a 2D screen, so I'm not even going to try. But I am literally talking about like a spatial dimension here. So that continues, okay, and pretty much after 3 dimensions, we just throw the word hyper on stuff. So hyper is like a throw-all term for higher dimensional. So any of these like hyper surfaces, if there's n inputs to it, then it lives in 1 dimension up from the amount of inputs, right? Which kind of makes sense, because like if you think of like, the math that well, like if you're plugging in this green, x values on the x-axis, then you plot them on the red one, at different heights and whatnot in the y values. So you have only 1 input, but it's graphed in 2D space. If you have 2 inputs, you're going to graph it in 1 dimension higher, or 3. 3 inputs are 4. N inputs, n plus 1. So this thing is actually graphed in there's 8. That's like what it would show up in, basically. And a lot of times after, even 3D, we don't bother trying to think about what they look like. There's some problems in math where I've been basically asked to try to think about what a 4-dimensional thing looks like, but it's pretty rare. It's not super useful to like everyday kind of math and science. So you won't really be asked to do much past this. So this is a way that we can kind of start to think about what things, like what functions look like. This is basically just the idea of like traces. And it's sort of it really is just a trace. It's like a special type of a trace. So it's called a level curve. And basically what you do is you specifically are setting the like f of x comma y, the z part, right? So you're setting that to equal to a constant, and then you draw what it is from there. And you actually know these things well. So like topographic maps are actually level curves. And, you could look at a 2D map down here, like these lines, and if you have some instructions for like what what heights they are, you could start to visualize, this mountain that kind of sits above the, level curves of the, in 2D down here. And this might be a certain mathematician's voice that you're hearing their arm. This is my arm. And I actually have a mountain from the place where I grew up, and it's a long story as to why I've got a tattoo of a mountain on my arm. But it's the same idea. It's like this is, the bold lines can represent like different, kind of milestones with the z height, let's say. And you can just get these different level curves by setting z equal to different things, right? Like if you set z equal to, I don't know, what is this, like 20, it looks like in the picture you get this line. But then if you set z equal to like 45, you get this upper one. So I'm going to show you how we can kind of do this to get an idea of what some stuff looks like. But basically we're just setting specifically the output, the f of x comma y equal to a number. And then we're like going to like think about what it looks like from there in order to get an idea of what the thing looks like in real life. So I did say 2 seconds ago I'm not going to give you things in 4 dimensions too often, but I do this example because this trick of using level surfaces is actually used most often for things that we can't draw. So this is a 4-dimensional object, and it's 4-dimensional because like you plug in x, y, z, and you get out, some new variable, f of x comma y comma z. There's 4 things kind of going on there, right? And the idea is like try to think about what this would look like in 4 dimensions. And the way that we sometimes do this is we basically take like a slice in a sense, and we think about what does a level surface of it look like, if we cut it off at a certain, let's say that's called a height, although I don't know what we would call that last dimension in 4D space. But basically a different 4-dimensional space cutoffs, what does this thing look like? So if you just pick, some different values, I'll show you kind of the idea here. So if you let basically f of x, y, z equal 1, then you actually get something that you should all know pretty well, which is just we'll call it the unit sphere. So you would get this red sphere in here. It's a sphere of radius 1. If you chopped off z, it's literally a circle of radius 1. There's not much else to say about that. If you let f of x, y, z equal, let's say 4, then you get 4 equals x squared plus y squared plus z squared. And you would get just this yellow one. The whole is here just purely to show you what the thing inside is, but you would basically be fully encapsulating the, red, pink kind of colored sphere with that yellow one. And you could keep doing this, right? You could have a different level surface. And it is specifically actually here called a level surface, not a curve, because they're surfaces. But if you plug in a different constant, you're just basically going to increase the radius of that sphere, and they just look like they're, kind of like one of those dolls where you have like the little stacking dolls and the smallest dolls inside. Now, what's weird is actually in 4 dimensions, it doesn't look like this. This thing would actually not have you wouldn't be able to perceive it as, fully enclosing the other one, and that's not something that we need to basically get into. But the level surfaces here are literally spheres. That's all I just kind of want you to see. If you just set the output, f of x, y, z here, equal to different constants, like 1, 4, 9, whatever, you're going to basically get spheres of larger and larger and larger radiuses. All right. So this one's a little bit easier to actually get an idea of. So if we have this function, I hope that you realize this is just a plane, z equals 6 minus 3x minus 2y. And hopefully our brains are pretty good at visualizing what that would look like. But just to show you that it kind of agrees with it, I'm going to basically sketch level curves, which are actually going to be lines, because that's what planes would look like in 2 dimensions, at these different constant values. So if we do negative 6 equals 6 minus 3x minus 2y, right, we would get minus 12 equals minus 3x minus 2y. And I guess I'll just do it here. And then I'm going to sketch this thing. So if you plot the intercept in x, you would get 4, and the intercept for y would be like 6. So you'd specifically get that level curve, which is a curve of curvature 0. And then let's just I think you guys get the idea of this pretty well. I'm just going to do, literally one more. So if you do 0 equals 6 minus 3x minus 2y. So I'm just setting, this f of x comma y equal to 0. So move the 6 over, and then if you plot the x-intercept here, you're going to get 2, and then the y-intercept would be 3. So you'd get this, 1 for that. So you could keep doing this. You know, I'm not going to go through all of them. I think, honestly, it's doing 2 more is kind of overkill. But basically, you're going to get lines, you know, that are parallel like this. And you could even get ones in between here and whatnot. So you would get all these different lines, and that's just because if you, like, take the cross-section of a plane, you get a linear thing like that. And these really are called curves. They're called level curves when you draw them in 2D. They're called level surfaces when you draw them in 3D. But it's our way to kind of visualize what something looks like in higher dimensions, just like a topographic map does. So these last 2 slides here, so I have these weird functions of 2 variables, and they actually are things that you've kind of seen before, but if we were in person, I would show you using either Desmos or Math 3D. I can show you what these things look like, but I can't really do it here, so I'm actually going to make a separate video and attach it to this where I explain how I can kind of go through different C values and get different surfaces. So I'm going to do it for this, and if the video doesn't run too long, I'm also going to actually do it for this one too. So these are both things that are kind of fun to play around with on Desmos and Math 3D, and you can kind of get an idea of what the thing might look like in a higher dimension just by looking at like different level curves of it. So basically I can go to like Desmos and I can be like, okay, what does 2 equal e to the cx squared plus y squared look like for different c's? And then I can do like 3 equals e to the cx squared plus y squared and whatnot. And you'll see that there's like different 2-dimensional curves basically that arise and kind of give you an idea of what it might look like in 3D. But it's too hard to do in here, so I'm going to have to make another video for that.